In problem 13.52, we got a monkey wrench and it's pivoting at 2.5 meters from its center of mass. So here's our wrench, poorly drawn. It's pivoting. Here's our pivot point up here, and it's 2.5 or 0.0250 meters from its center of mass. This apparently is our center of mass. Okay, swinging back and forth, and its period for small angle oscillations is 0.94 seconds. So they want to know the moment of inertia. Well, the equation for moment of inertia for a physical pendulum is T equals 2 pi square root of I over mgx, where x is the distance from the center of mass to the pivot point. So I'm looking for I, so I'm going to take this first, I'm going to square both sides. So I have t squared equals 4 pi squared I over mgx. I'm going to rearrange it just to solve for I. So I is going to be t squared times mgx over 4 pi squared. Now I'm going to plug in all the information that was given to me. 0.94 seconds squared. The mass of the monkey wrench is given to me up at the top, 1.80 kilograms. G is just 9.8 meters per second squared. And X is just going to be our 25 centimeters, 0.250 meters. And all that's going to be divided by 4 pi squared. That's going to be I. It's going to equal to all that. I want to point out that our seconds are going to divide up with seconds squared because it's squared also. We're going to left with just kilograms, meters, and meters. So we're going to have a number that's in kilograms, meters per squared. We're going to like that because that's what we want our number for. We want our number for moment of inertia to be, and it's a small one, 0.00 or sorry, 988. Sorry. Oh, 988. Sorry, I'm having trouble writing this one. 988 kilogram meters per second squared. Kilograms meters squared, sorry. That's going to be our moment of inertia. In part B of the problem, they're telling us that our wrench, which I'm going to draw again here, maybe. Okay. Yep, there we go. They tell us that our wrench is displaced, and they tell us how many radians it's displaced. That's in here, 0.400 radians. Okay. And then they're going to let it swing this way, and they want to know what is the angular speed at the middle. Okay. Well, if we're dropping it, it's going to be an energy conservation problem. But it's going to be the kind that we're sort of used to, okay? Except that we're looking for how far the center of mass drops. So remember, our center of mass is here. It's 0.25 meters from there. And when it swings down, it's going to drop down. Put this in this. When it drops down, if this is what our guy is going to be at the bottom. Sorry, no, it doesn't look the same. It'll be down here. So the actual drop in our center of mass is going to be this much. Okay. So the actual height that's going to be, that it has in terms of MGH is going to be that much, which is going to be a little different than normal because we're going to actually have to measure like this part up here. We're going to have to actually subtract that from this whole distance here. Okay. So let's do that over here. Okay. We know that the distance that I drew just in black is just going to be x. Okay. And the distance that I drew in blue is going to be the little bit here. Okay. Since the angle is known, okay, and we know the hypotenuse, it's going to be minus x times the cosine of the angle, which is going to be in radians. That's going to be the height that it falls through as it goes. So again, we're going to conserve energy. E equals E prime. And for us, that's going to mean that we don't have any potential energy, but I'm going to say K plus U equals K prime plus U prime. Okay. And we're going to say this is equal to 0 because it's still. And this is going to be equal to 0 at the bottom, right? Okay. So we can solve for this. It's going to be mg x minus x cosine theta. And that's going to be equal to the kinetic energy at the bottom. Again, it's not moving translationally. It's only moving rotationally. So it's only rotational we have to care about. So it's 1/2 I omega squared. Okay. I'm going to move everything over a little bit. So I'm going to have 2 mg. I'm going to factor out an x because that's convenient. 1 minus cosine theta. All that divided by I. If I take the square root of all that stuff, it should give me omega. Okay. If you need a second to wrap your head around all that factoring, go ahead and pause and take a second look. Okay. I'm going to plug all that stuff in down here. Okay. And omega is going to be the big square root of 2. Again, it's going to be a 1.80 kilograms, same mass as in the first half. Okay. 9.8 meters per second squared. Okay, x is going to be that same 0.25 meters. And it's going to be 1 minus the cosine of 0.4 radians. It's important to remember your calculator needs to be in radian mode to do that. And for this moment of inertia at the bottom of the fraction under the denominator, we solved for that before, 0.0988. Remember, I couldn't write that kilogram meter squared. I couldn't write that last 8. That was annoying. So the kilograms are going to go away. Both meters are going to go away. I'm going to have 1 over second squared, which is good. And then that's just going to be, so then I'm going to end up with, when I solve it all out, I get 2.66. That's 1 over second squared, which is just going to be 1 over seconds when I take the square root. And it's going to be radians per second. Sorry, that D didn't turn out so good. That's better. Oops. There we go. So radians per second. So that's the speed at which it actually left the, or got to the wrench got to the bottom of that pivot.